Okay, question number 4 from 2024. This one is a bit of a long one. I think this is probably going to take quite a long time. So, just go to the bit that you need. You shouldn't have to work the whole thing all the way through necessarily, but that's what I'm going to do anyway. So, we have got this contrast agent that we want to get to, which was shown later on down here. Alright, but let's not get ahead of ourselves. We want to do this synthesis part. So we want A, B, C and D. So this SOCl2, very, very common in the Olympiad. It gets used to switch out the alcohol part, in this case the alcohol part of this carboxylic acid, and just replace it with chlorine, just to make that a better leaving group. So all we're going to do, you can, I'm not going to bother, but you can work out the molecular formula here and you'll see that the only difference is that you're taking the OH off and putting the Cl on. So I'm going to get ClO, Cl, and then double check the molecular formula. So 1, 2, 3, 4, 5 carbons, 1, 2, 3, 4, 5 hydrogens, bromine, 2 chlorines, 2 oxygens. Okay, and then so you should be fairly confident that if I were to ignore that step and just react the alcohol with the carboxylic acid, that would give me an esterification reaction. So you can expect B to just be excuse me, to just be the ester. Now there's probably a few reasons why they do it like this. It's probably makes this slightly more reactive. It might make it so that if you do the acid with the alcohol, that's going to set up an equilibrium. Whereas if you replace it and do the chlorines and now react that with the alcohol, that's not going to be an equilibrium. That's just going to go to completion. But you get the same product anyway. So I'm going to get my O. It's going to be the same thing here. And then I'm going to get my ester groups on the end. All right. And if you want, you can start looking down here and well, actually no, this doesn't give you any information. But you can see, you should be able to see at this point that this part of this final thing is what we're looking at the moment. All right. So here we have NaBH4 standard reduction. So if I reduce the acid, now you'll probably be familiar with the reaction of an acid becoming a aldehyde. In this case, if you draw out the aldehyde, you should get that. So you may be tempted to give this as your answer for this step here, but you should always check the molecular formula, which is why they've given it in this case, and you'll notice that it doesn't quite match up because I don't have quite enough hydrogens, suggesting that I've gone one step further. And they do actually state in the mark scheme that usually this isn't a strong enough reducing agent, but because of the pyridine ring, it does work. But you don't need to know that because you would have checked it with the molecular formula, realised that this can't be correct, so thought to yourself, okay, well, if I've gone from acid to aldehyde, what if I reduce it one step further to the alcohol, even though that might not be what I exactly expect? Do I get the correct molecular formula? And the answer is yes, you do. Because now I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 hydrogens. So I've got my molecular formula that I want. And then PBBr3. So all I've done is I've changed 2 hydrogens, 2 oxygens for 2 bromines. So no great difficulty working out what's going on there. I feel like for organic synthesis questions on the Olympiad, that's probably about as easy as you're going to get. Yep. Then we are asked to circle the stereocenters on the structure of compound H and N-suboxylate. This one always, it doesn't matter how much you go over this in class with students, they always seem to have a bit of trouble with this. So you're looking for carbons, so carbons that are bonded to 4 different groups. All right. I remember when I marked this for my students, lots of people were going for the nitrogens maybe. I think they were getting some confusion there, or for very common going for an sp2 hybridized. It's just not going to happen because that's trigonal planar. It's not going to bond. It's only bonded to 3 different things. So you should be able to see that this one here, all right, is bonded to this acid group here, this carbon chain and the nitrogen, and then the other one is your, whatever it is, your hydrogen there, however you want to draw it. Okay, and then I've got all 3 of them like that. I feel like they're quite generous with the 2 marks here, given that all 3 centres are essentially the same. But anyway, okay, then we carry on with the synthesis. So we now want E to G. Okay, so I've got this amine, then I've got this tosyl thing, and then you can see that what's happened is D. So D up here gets brought in at some point. D is this. So this pyridine ring, that's the benzene ring with the nitrogen in it, that's there. Okay, and then I've got my 3 nitrogens around. So that's how they're building up this molecule. And then they bring in B here, and that gets added on. All right. So molecular formula wise, you can see that the reaction of this and this is giving me C25. Now, there's not 25 carbons in these 2, so I'm obviously getting a multiple reaction with one of them. Okay, this has got 1, 2, 3, 4, 5, 6, 7. All right, so that's got 7 carbons in it. This has got 1, 2, 3, 4 carbons in it. Okay, so, well, what's 3 times 7 plus 4? It's 25. So it's going to be 3 of these reacting with 1 of these, which makes sense because it's going to react each time with each individual amine. Okay, so this needs to be a little bit careful about how you draw this. All right, because this way of drawing it is not that helpful. So I'm going to draw it like this. And obviously it's the chlorine. All right, that's going to come off. So more or less what's happening is your amine is going to be coming in to the sulfur, and then the chlorine is going to be coming off. All right. So my N is bonded to my sulfur. Nothing else changes. All right. Now I remember when this was done a couple of years ago, lots of students forgot this extra methyl group on the end, or they missed out the sulfur or something. You know, there's lots of little mistakes that got made. Or they got the number of carbons here wrong. They went carbon and then nitrogen, where actually it's 2 carbons. All right, so I'm going to do my N there, and then I've got another one. This is going to get messy. You know, because you make any mistake here, just because you've got the methyl group here and the methyl group here, if you miss the methyl group on the other one, you know, it's that kind of carelessness that's going to cost you the mark. All right, so then we have that, and that's going to have a hydrogen, and that's going to have a hydrogen. All right, so at this point, you want to go ahead and double check your molecular formula. So do I have 25 carbons? Well, each of these is 7. 7, 7, 7, 21, 22, 23, 24, 25. Fine. What else do I got? 31 hydrogens. Okay, we'll be here all day counting these. So 3, 4, 5, 6, 7. All right, so 7, 7, 7, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. 3 nitrogens, 1, 2, 3. 6 oxygens, 2, 4, 6. And my 3 sulfurs. Yeah, okay, so we're good to go. Then we bring in D, which remember I said was this thing here. Okay, and we have to look a little bit ahead here. So we're going to make F, that's what we want. Now the difference is that all of these tosyl groups, all these sulfurs with the benzene rings on, they've all gone. So it's safe to assume that this step here is just the removal of these from the nitrogens, which means that this is going to be this thing, but with these things still attached. Okay, so I'm going to draw my structure for D down here. Okay, now I've got carbon and I've got carbon. Alright, now what happens is when the nitrogens from the amines come in, they're going to kick off these bromines. Alright, so I'm going to be bonded next to a nitrogen and to a nitrogen. Okay, now those two nitrogens there, zoom this out a little bit, those two nitrogens here are these two nitrogens. So you can see that these are sort of coming round, or you can imagine my D coming in here like this, and then these are coming round and they're going to kick off the bromines. Alright, and then I've got two carbons, 1, 2, and then I've got my nitrogen, and two carbons, and then I've got my nitrogen. Alright, and you'll see that that looks a lot like this. Okay, but I haven't done the step where I remove these yet. So that's what's still, ooh, you can see there, if you're a little bit too fast, you might make a mistake. Okay. Alright, so that's that. And then we do the reaction with the acid and the sodium hydroxide, and it takes off these tosyl groups. Okay, and then we go down to G. Now G is the reaction with B. Okay, so I'm reacting this with this. Alright, and all that's going to happen here is the nitrogen is going to attack this carbon here, bond to the carbon chain and kick off the bromine, which is then you see, instead of being a bromine here, I'm now bonding to my nitrogen. This final step here is the ester hydrolysis. So you'll notice that the difference between this here is that I've removed my ester group to go back to the carboxylic acid. So G really is just going to be this, but all these alcohols are still esters. Alright, so all I need to do is just redraw that. Alright, so these molecules are massive, you know, which you probably don't have, you might not have as much experience drawing such huge molecules, and that can be a little bit disconcerting at first, but the chemistry should be easy enough to understand. Again, remember here it's only one carbon, but then here it is two carbons. Oops. Alright, and then I've got to my esters, and then I'm constantly, you can't see me doing it, but I'm constantly referring down to this to make sure I'm getting all the correct number of carbons and everything, like that, and then same here. So we're going to go, and instead of the acid I've got the ester, and then I've got 1, 2, and then my ester again, like that, and then one more. I'm going to get this too messy. Okay, like that. Okay, so that's the end of that part of the question. Now, at this point, it's probably worth trying to think, what is going on? What is this chemistry about? You don't need to know why any of these steps are done in order to get the marks, but if you do understand it, it probably helps a little bit. Okay, so why are we adding, we add this here to this, then do the reaction, then remove it. Likewise, we turn the alcohol into an ester only for it to be turned back at the end. Right? These are protecting groups. So here, this is being used as a protecting group. So what that means is by converting this to this, I'm protecting the amines. Essentially, what it does is it means that this amine here cannot react with my pyridine ring molecule, right? So it stops this nitrogen here from attaching here, right? And it stops multiple reactions, because if you think this amine here can react twice, so in theory it could react twice with the pyridine ring molecule D that I'm bringing in. All right. So what I do is I use the tyrosine group to protect my amines while I do the reaction, and likewise with the esterification as well. So if you want to know more about that, you can look at protecting group chemistry. It's not really something that we've learned at this level, but that is what is being done here. Okay, so then they give you very nicely the rest of the synthesis, although it doesn't seem to be too important for the rest of the question. So compound H, what we just found, is converted into gadopiclinol, which is the contrasting agent, and the average dose of gadopiclinol is 6 centimeters cubed of an aqueous solution of concentration 485.05 grams per decimeter cubed. And then we are asked to calculate the mass of the element gadolinium required per dose in milligrams. So my dose is 6 centimeters cubed, and the concentration is 485.05 grams per decimeter cubed. Okay, so if I have a litre, it's 485 grams, but I've only got 6 centimeters cubed. Okay, so how am I going to do this? Well, there's probably a few ways that you can do it. The way that I'm going to do it, because I've been given my dose, my concentration in grams per decimeter cubed, I'm going to work out the mass of gadopiclinol in 6 centimeters cubed, and then I'm going to work out the mass of gadolinium as a fraction of gadopiclinol. I think at some point, it doesn't matter how you do this, you're going to have to work out the molecular mass of gadopiclinol. Luckily, you don't need to worry about this because you are given the molecular formula earlier in the question. So, if I have 485.05, that's in decimeters cubed, times by 6. That's going to give me my mass in my dose. So if I go 485.05 divided by 1,000 times 6, I get 2.9103. So that's the mass of gadopiclinol in my dose, and I'm going to now multiply that by the fraction of gadolinium. So I've got 1 gadolinium, 157.25, divided by the molar mass. Now I'm not going to spend all the time working out the molar mass. Well, I am, but I'm not going to write it all out. It's 970.102 is the molar mass. So if I've got 2.9103 grams of my gadopiclinol, how much gadolinium is there? It's just a fraction. So if I do 2.9103 multiplied by 157.25 divided by 970.102, I get a calculator error 2.9103 times 157.25 divided by 970.102. I get 0.4717 grams of gadolinium. But I'm asked to do it in milligrams, so that's 472 milligrams. There is probably another way of doing it. I think the mark scheme, when I checked, did it a slightly different way, but that's the way that makes most sense for me. Then we have this information about how it works in the MRI machine, which is very interesting, and you should read it if you're interested. And even if you're not, it's I'm not really sure. It's the kind of thing where you need to be really careful. Obviously, there's a very strict time limit, and people always run out of time while they're doing the Olympiad. This kind of thing here is that you need to be smart and realise that this isn't that. It's interesting, but it's not important. So if you've got nothing better to do, have a nice read of it. If you're really trying to maximise the remarks, then you need to read this and think, I don't need to spend too much time worrying about what this says. What type of electromagnetic radiation would be required to do this? Well, it's NMR. You were told right at the start of the question this is NMR, and you should know that NMR is radio waves. Okay, because the energy required to flip these hydrogen nuclei spins is tiny, so you need very, very weak radiation to do it. All right. Okay. Then we have, again, I'm not going to go and try and explain all the science behind this. I just want to make sure that you know how to do the actual questions themselves. Calculate the net magnetization, which is M, as a percentage of M0 before the pulse. So this is after the pulse at time t, this is before the pulse, at a time of 3 tau. All right, so all you've got to do is just replace t with 3 tau, which is very simple. So you're just going to have 1 minus e to the 3 tau over tau, which is 1 minus e to the minus 3. So if you just do that, so it's minus 3, 1 minus that, I get 0.95. Okay, but I am asked as a percentage, so you want to go for 95%. All right, so your M is 95% of M0. Okay, and that's how you would get the net magnetization is your initial magnetization multiplied by this factor here, and that's going to be 95%. Okay, then we have lots more information about this process. Again, I'm not going to waste time. Well, it's not a waste of time. I'm not going to spend time now going through this. We're just going to go straight to the question. So, calculate chi if the molar concentration of gadopiclinol at the image site is 0.05. Assume the density of water in the tissue is 1 kilogram per decimeter cubed. So, chi is just this mole fraction thing. All right. So it's the moles of gadopiclinol divided by the moles of water, and the concentration is 0.05 in a decimeter cubed. So really, I can just do 0.05 moles. All right. And then all I need here is the moles of water in 1 decimeter cubed, right? Because if it's 0.05 moles in a litre, then I just do 0.05 divided by the moles of water in a litre. And you're given the density, so you know that you've got 1,000 grams, so it then becomes quite straightforward. So the moles, I'm going to do my moles of gadopiclinol equals 0.05, and then my moles of water is going to be 1,000 grams divided by 18.001. 18.001, it's 1.008 times 2, so 16. Okay, it's going to give me 1,000 divided by 18.08. It should come out about 55. Yeah, 55.5. So then chi is going to be 0.05 divided by 55.5 to give me 0.0009008, okay, or 9 times 10 to the minus 4. So it's a mole fraction, which means there's no units, so that is our answer. Okay. So, assume that the overall reaction time of tau is described by tau C, tau E. So this is where we get quite mathematical now. We're asked to express the field-independent relaxation time, tau C, in terms of B1, B2, tau 1, tau 2. Now, they've been a little bit cheeky here, and they're giving you this. Now, obviously, if tau E is directly proportional to 1 over B squared, then tau E is equal to K over B squared. All right. Now, if I've got tau 1 and tau 2 are 2 different magnetic field strengths. Okay, so I can write tau 1 equals something and tau 2 equals something. Now tau c, the relaxation time, does not depend on the magnetic field strength. So tau 1 and tau 2 are two different magnetic field strengths, but tau c does not depend on that. So I can just do tau c, whereas tau e does change. Okay, tau e does change. So I could write here sort of tau e1 and tau e2, but I know that tau e is equal to k over b squared. K is a constant, b is my magnetic field strength, so I can just write k over b1 squared and k over b2 squared. Okay, now what I want is I want tau c in terms of b1, b2, tau 1 and tau 2. So what I'm going to do is I'm going to rearrange these equations to try and get rid of my k's. I don't want any k in there. So if I multiply through by b1 here, I'm going to get b1 squared tau 1 equals b1 squared tau c plus k, and then here I'm going to get the same thing, b2 squared tau 2 equals b2 squared tau c. Now these suffixes here could start looking similar, so try and be careful. Then I can get rid of my k's however you want, it's up to you. I'm just going to subtract one from the other, so I'm going to do b1 squared tau 1 minus b2 squared tau 2 equals b1 squared tau c minus b2 squared tau c, and then my k's cancel. All right, and then I can factorize my tau c here to get b1 squared minus b2 squared, and then I do rearrange for tau c. So I should get, obviously when you do this you should do it all your working here in this massive box they give you, what I should have done. But I'm going to get tau c is equal to b1 squared tau 1 minus b2 squared tau 2 divided by b1 squared minus b2 squared, which is a lot of work for just 1 mark, but this is a chemistry test, not a maths test, and this is the kind of thing where you can get that, you know, the question could start here and you could have no knowledge of chemistry and just do the maths. Alright, so it seems fair enough that they're only going to give you 1 mark for that. Okay, then at low temperature, this is where it starts to get a little bit hairy. Tau c is 1 over q chi rc, where q is the number of water molecules coordinated to gadolinium and rc is the rate at which the coordinated water is exchanged with the solvent. Which makes sense because those are the things that you were told affects the rate of the relaxation. Again, at this point it's really difficult to sort of keep in mind all the new chemistry that you're learning about gadolinium and these contrast agents and manipulating all the maths that you're being asked to manipulate. But it's nice if you can go back afterwards and try and work out what it all actually means in the end. So, we are told we've got this equation for tau c. Q and chi are just numbers, and then RC is given by this equation, and we're asked to give an expression for tau c in the form y. So we're going to linearize it, and we want y as a function of tau c and t, and the coefficients a and b in terms of q, chi, a, delta h, and r. Okay, so where to start? Luckily, they give you a huge bit of working space here. So let's see if we can't figure out what's going on. All right, so first things first, I'm going to write tau c, which is 1 over q chi rc. And my rc is a t e to the minus delta h over rt. If I just put this expression for rc into here, what do I get? So I get tau c equals 1 over q chi a t e to the minus delta h over rt. Does this look like it's the way to go? I think so. We were told that we want y in terms of tau c and t, so I can multiply it up here. So I'm going to get t tau c is, and then I want my exponential to be, well, my exponential here is in the denominator, but it's a negative, so I can put it up top. So I can have e to the delta h over rt multiplied by 1 over q chi a. Alright, and then if I take the log of both sides, log t tau c equals delta h over rt plus log 1 over q chi a. Now if you're not, if you like maths and you're really good at maths, this is probably going to be quite straightforward for you. If you're not, this should be quite similar in feeling to when you linearize the Arrhenius equation. If you know the normal form of the Arrhenius equation, so the normal form, k equals a e to the minus e a over rt, and you should be familiar with the linearized form, which has got a logarithm in it, you should be able to do that linearization. So you should be able to do log k equals log a plus log of e to the minus e a over rt and get the linear form. So you should be confident with that little bit of maths. Okay, so we should be more or less, I think that might actually just be the answer. So if I compare it to the form that I was asked to give it as y equals a over t plus b. Yeah, so my y equals log t tau c. My a is delta h over r, and my b is log 1 over q chi a. Okay, so some low temperature values of tau c are given in the table below. Using the result of part I or any of the means, calculate the value of aqx. So aq chi. So we want to find this here, but essentially we're being asked to find b. Now we're told t and tau c. So we're told what y is, more or less, and we're being asked to work out what b is. So we need to get rid of a somehow. Alright, so what I've got, just like you would with the Arrhenius equation, you're going to have y equals a over t plus b. Now a and b don't change with temperature, so if I have T1 I can have Y1, and Y2 is going to come at T2, so I'm going to get that. Now remember, I'm being asked to work out the value of b because I'm being asked to work out q chi a, so I need to know what this is. So I'm given my temperatures and I'm given my y values, so I need to get rid of my a values. So I'm going to rearrange these equations to give me T1 Y1 equals a plus b T1, and T2 Y2 is a plus b T2, and then I just want to get rid of my a's. So I'm going to do, let's do the similar thing to we did earlier in the question. T1 Y1 minus T2 Y2 equals my a's cancel, and I get b T1 minus b T2. Factorize this to give me b T1 minus T2, then I write out b equals T1 Y1 minus T2 Y2, all divided by T1 minus T2. Okay, so that is an equation for b, and then I just put the numbers in. So my numbers are over here. So this is going to be it's going to be pretty tricky, because remember my T1 is going to be 275, but then my Y1, remember, y1 is going to be the log of 275 times that. Alright, so maybe I'll work those out individually. So maybe I'll have another, let's just have here y, which equals log t tau c. Okay, so those are my values for y, and then I need to multiply each one by the temperature again. So this is going to be, I'm just going to do it. So those are my, if I take the numbers that I worked out and multiply them by the temperatures, I get those, and then I divide that by 275 minus 280, and if I work all of that out, I get that. Alright, so that's my B. So in other words, that is log 1 over q chi a. But I am asked to work out what q chi a is. Yeah, because it says calculate a q chi, so I just need to do a little bit of rearranging. So if I take the exponential of that and the reciprocal, I get q chi a is 1.73 1, 2, 3, 4, 5, 6, 7, 8 times 10 to the power of 9. And I'll write the units on as you were given them. There you go. So, again, that's some, I mean, there's no individual step that's really that difficult, but putting it all together is quite hard work. And then we're still not done. Applying a similar approach to exchange rates at high temperature, it's been calculated that A over Q chi is that. Use this information in your previous results to calculate Q, the average number of water molecules coordinated gadopiclinol. So, this is a very strange question because I want to work out Q. And I am told a value for A, Q, chi. So, do I have a value for A and a value for chi? Well, no. I mean, I have a value for one of them, and that is, I know that chi is 9 times 10 to the minus 4. And A, Q, chi is what I've just worked out. So, essentially, what I've got to do is, and you can see because here you're given a value for chi and a value for A, Q, chi. So, I've got to use A over Q chi, and A Q chi to work out Q. Alright, I know it's a bit of a mouthful. So I know A over Q chi. I know chi. And I know A Q chi. And I want to work out Q. Alright? So, how do I do it? Well, let's just try a couple of things, see what happens. Let's say if I do A Q chi divided by chi is going to give me A Q. I need to get rid of the A. So if I do A Q multiplied by Q chi over A, which is this turned upside down, I'm going to get Q squared chi, which I can then divide by chi and take the square root. Alright, so let's try that. So if I do AQ chi, so 1.73 times 10 to the power of 9, divide by chi, which was 9 times 10 to the power of minus 4, that's going to give me AQ. Okay, so if I work that out, I get 1.73 exponential 9 divided by 9 exponential minus 4, I get 1.92 times 10 to the power of 12. And then I'm going to say q squared chi is equal to aq divided by a over q chi. Just multiplying it by the other way, right? So it's going to be 1.92 times 10 to the power of 12 divided by the number I was just given in the question, which is 6.618 times 10 to the power of 14. Okay, so if I do that, divide that by 6.618 exponential power of 14, I get 0.0029. Then q squared is going to be 0.0029 divided by 9 times 10 to the power of minus 4. So divide by that gives me 3.227, and then q is just the square root of that. So if I do the root of that, I get 1.796. Which is an answer that sort of makes sense, right? Because it's the number of water molecules, average number of water molecules. I'm not really sure what they're getting at with this last question. I think they do it slightly differently in the mark scheme, but it's the same kind of philosophy. You're just trying to work out. It's just algebra, right? I don't really know what they're doing, but that's how you can do it. Like I said, bit of a long one, so good luck.